All right. Good evening, ladies and gentlemen. Welcome to the Europlanet webinar on the ExoMars landing. Actually, the first part of the ExoMars landing, to be more precise. And my name is Gernot Groemer. I will be the host for tonight, and I have a very special guest with me today. Jonathan Morrison, UK-born 1967. He's a senior scientist responsible for the planetary environment facilities at the Institute of Physics and Astronomy at the university in Aarhus, which means he is hailing from Denmark. Good evening, John. How are you doing?
Hello, pretty good, pretty good.
Good to have you with us. John, can you give us a little bit of a context of who you are and what you do, and most importantly, what your relationship to the ExoMars mission is in general?
So I run a laboratory here where we try to simulate another planet. So this big red chamber behind me, we can pump our atmosphere out and recreate, for example, a Martian environment.
That's the reason why it's red.
Yeah, and we had to paint it red, obviously. So, and so my role with the ExoMars mission generally is involved in testing. So what we can do is, for example, ESA can come with different parts of the land that they're building, instruments, or even parts of rovers, for example. They can put them then in our chamber, and we can recreate Mars, and we can test that everything functions the way it should do.
When you say recreating Mars, that means what kind of environmental parameters are you changing as opposed to testing on Earth?
So there's low pressure on Mars. There's only about 1% of the pressure that we have here. So basically, we have to pump it out, and the composition is completely different. It's almost pure CO2. So we pump our atmosphere out and we fill in a tiny bit of CO2 gas. And it's also cold on Mars. It's generally only around -60 on the surface. It varies quite a lot, but we also have a cooling system. So we can essentially cool the entire inner part of our chamber to around -60 degrees.
When you're not testing Mars rovers or components of Mars rovers or landers, as we talk about in a couple of minutes or so, you are very much focused on Mars, I understand. So your research background is not so much in the engineering part, but more on the planetology side. Can you tell us a little bit about what your specialization is and what is your, where your heart goes from a scientist point of view?
Well, one important aspect that we can recreate in this chamber is that it's a wind tunnel. So down this end, if you can see it down there, there is essentially a fan system up here, and we can recirculate the air inside this chamber, and then we can inject dust that looks like the dust that we see on Mars. So a lot of my own research is to do with studying dust particles and how they interact in the atmosphere. And it's not just to do with Mars, it's to do with basically any planetary atmosphere. So dust and ash on Earth, we do a lot of investigations with that. And we've done a lot of studies of the Martian dust. How it's transported and what it looked like. And this is also to do with some of the testing that we do here. So for example, we can expose components that they think might be sensitive to dust. We can expose them to dust that under the same conditions that it will be on Mars. For example, solar panels obviously will get dust on them. So that's the kind of testing that we can do for them.
Yeah, we always say in the Austrian Space Forum that dust is the natural enemy of the engineer on Mars, as far as I understand. And that's the reason why we're also spending quite some efforts when we build our own spacesuit simulators to take care of the dust load as well. I think before we go into details of ExoMars, especially for the viewers who are not so familiar with the planet itself, maybe it's a good point now to give a little bit of a frame of reference on this planet, which could be considered the most Earth-like planet. It's about half the size of the Earth, which means you have about 1/3 of the gravity level. You said already there's little air, which means we are talking about 5, 7, 10, 11 millibar or so, mostly comprised of carbon dioxide. It's very cold, typical temperatures around an average -70 degrees Celsius. It doesn't look very hospitable or habitable at this point. Even the surface is chemically pretty reactive. However, we have good reason to assume that it wasn't like this all the time. We know that Mars had liquid water on its surface, maybe even oceans up to like 3.5 billion years ago or so. We even see indications of ancient shorelines nowadays. So it seems Mars was much warmer, much more habitable, I would say. John, how do you see this?
Yeah, that seems to be the case. But now it does seem to be that Mars is the interesting thing about Mars is that although it seems cold and dry, it's actually got a lot of water on it. If you melted all the water on Mars, it would be about 10 meters deep over the whole planet. So it's not that there isn't any water, it's dry and dusty because it's cold. So I think this is the major environmental aspect of Mars that happened at some point. At some point, it seems to be that Mars lost quite a lot of its atmosphere, and then the temperature fell, and so it's kind of in hibernation. So it's
a frozen world.
It's a frozen world. Yeah. But the important thing, I think, for habitation is that the raw materials for humans surviving are still there. There's water there, and even though the atmosphere is thin, it's still an atmosphere. It'll still protect you in many ways.
Absolutely. If we come back a little bit to the planetology part, you say most of the atmosphere is comprised of carbon dioxide. However, if you look into the trace gases and the diminutive components of the Martian atmosphere, there's one species of molecules which really caught our attention already when the European Mars Express planetary Fourier spectrometer made its first measurements, and our French colleague came up with a pretty spectacular discovery, which was just on the brink of what the instrument can do, this planetary Fourier spectrometer. And I think you know what I'm talking about already, the methane detection. So what is the fuss about the methane on Mars? We have methane on Earth emerging from cow stomachs and from Siberian permafrost, but we don't seem to be so concerned about the methane on Earth. So what's the difference on Mars then?
I think the thing that's interesting about methane is that it in principle is unstable. So unless something creates it in the atmosphere, then it can't have been hanging around a very long time. It essentially will oxidize. And so for many years, even before it was discovered on Mars, it would be seen as a sign, an indicator that possibly there's life. There may be other origins of the methane, but it certainly is one of the key things that you would look for in the atmosphere if you're to look for signs of bacterial activity. Methane would be sort of one of them. So first of all, and most importantly, we have to sort of confirm that there is methane in the atmosphere. It's still controversial. It's not every scientist is agreed that okay, this is 100% for sure. So this is an important thing that this mission maybe will be able to nail down. If they confirm that there is methane there, then we have to find out where it's coming from. And or it could be life, or it could be the planet is still geologically active and it's some kind of geological origin. Either way, it's very interesting.
Absolutely. I mean, I think there are even ways how to differentiate by the isotopic composition if it's a biological origin or a geological origin, and that's really interesting to know, because the sensitivity of the instruments has to be much better than what we had on Mars Express. I mean, Mars Express was not built specifically for methane, of course. It was just as a collateral scientific benefit to get those data, I would say. But that brings us exactly to the very mission which might be able to measure the methane by a factor of about 1,000 times more precise than the PSSs are, as I understand. Which brings us, of course, to ExoMars. I have to admit, when I first learned about ExoMars, I was a little bit confused that there was one mission, maybe a second one had the same name. So it took me some while to realize that this is in fact a twin mission, I would say. So John, why don't you talk us through the architecture of the ExoMars mission?
So this first 2016 mission is also split up into two parts. There's an orbiter, with a set of instruments on, as you were saying, analyzing the atmosphere mostly, but also imaging the surface. And then there's a lander part, and this lander part was originally designed as a first technologically developing mission to try to develop the knowledge and technology in Europe to be able to land something safely on the surface of Mars, which is very tricky. The success rate of landing something on Mars is not high. It's close to 50%. There have been a lot of lost missions. So it's a technological challenge, and that was essentially the purpose of this lander. More than the scientific, it was mainly to do with developing technology in order to send a mission later on, which now is going to be in 2020, to land a rover safely on Mars. So it's the rover really in 2020 that should do the major science.
On the ground. Yep.
On the ground, yes.
Yeah,
It should land and drive around a lot. And critically here, the one thing that this European 2020 ExoMars lander rover, the one thing that can do that hasn't been done before, it should be able to drill deeply down under the surface, around 2 meters or so. And that's in order to access possibly water ice and possibly also organics that haven't been destroyed on the surface.
If we come back to what's going on Mars right now, it seems to be quite an armada of spacecraft on Mars orbit. So we could always talk about an invasion from Earth, so to say, on a planet which is solely inhabited by robots at this moment. So I think every Transformer fan would be very happy at this moment. And it's been a pretty busy week in space activities in general. So we have three spacecraft with humans on board and a Martian landing as well. So everybody seems to be focusing so much on the fate of Caparelli and the lander at this moment. However, we must not forget that the major scientific activities will be not done on the ground at this moment, but they are done from orbit, by remote sensing. So, John, can you talk a little bit about the instrumentation of what the TGO is doing at this moment?
So it has a whole set of spectrometers in order to identify what chemicals are in the atmosphere, and as you say, possibly looking for methane. It also has a neutron detector built by the Russians, I believe, and that should analyze the ice. So help mapping the ice, subsurface ice, importantly, on Mars. And then also there's a camera system, which again, more and more orbiters being sent to Mars are having a very high resolution and extremely detailed imaging of the surface. And this is really, really helping to understand what's going on Mars in real time. I'm sure you've all seen some fantastic pictures of the surface of Mars. Well, this is the kind of stuff that will happen from this orbiter as well. There'll be some lovely pictures, I'm sure, come back, detailing what's happening on the surface. Yeah.
Besides the science, it also has a function as a relay orbiter, that for the 2020 rover mission, it will be a radio beacon, not a radio beacon, but a transceiver, basically, augmenting the signal and radiating it back to Earth, which is so far away that even the signal travel time varies in between somewhat 10 to 20 minutes, depending on the planetary constellations, which means it is certainly not a business as usual mission, but still something out of the extraordinary. So it's the second time Europe has sent an orbiter successfully into the Martian orbit. However, to be very precise, it's not fully there yet from the orbital dynamics point of view. I think it still has a couple of months or even a year ahead of it for some additional things before it finally arrives fully. So what's happening there?
Yeah, I think they need to stabilize the orbit and whatnot. But the point of this orbiter is that it's kind of an investment in the future. We want various options in order to be able to communicate between Earth and Mars, and this will be one extra one. NASA also has 3 different orbiters which also can communicate between Mars and Earth. And this is all good for the future because they do get old at some point, these orbiters, so we need to keep replacing them, and always to be able to have communication access between Earth and Mars in order to send all the data back. And especially when you're taking lots of really nice detailed images, I mean, that's a lot of data. So you kind of need the bandwidth. So
yeah, and that implies generations of PhD students to come to actually analyze those data. And I'm sure they're happily doing their PhD work on this in the next decade or so, I would say.
Yeah,
well, John, let's address the elephant in the room, and that is the landing of Caparelli. And, you know, I think this expression of this 6 to 7 minutes of terror is a very good one. It seems that the terror phase has been prolonged for much more than those 6-7 minutes in the meantime, and everybody is asking, what is the status of Caparelli? So first of all, John, can you tell us what we know for sure? What does the telemetry tell us at this point, and what is the condition of both TGO, which is doing the scientific mission, and the engineering demonstrator, Caparelli? So what happened? What was happening the last 24 hours on Mars?
As far as I know, the TGO is fine. It's functioning normally as they expect. But the lander, it did not progress. We should have had communication by now. The European Space Agency, as far as I understand, are still trying to communicate with it, and they have a lot of chances over the next few days still to communicate. I believe there will be 8 attempts every made to try to communicate with this lander that we still hope has landed safely. But as far as I understand, it does seem to indicate, by looking at the tracking of the lander, that the parachute detached too early, and then the rockets also stopped too early. And these two things together might indicate that it free fell the last section to the surface, and that would be bad, obviously.
So what would have been the nominal landing sequence? Before talking about what went wrong, can we hear about what should have happened? So what would have been the nominal landing sequence? Because I understand you're rushing in with more than 20,000 kilometers an hour. It's really hard to understand what this actually means. I mean, fast planes go, a tenth of that speed when we talk about fighter planes or so. This is 10 times a fighter plane, jet plane velocity, with a thing which cannot be controlled in real time by a human with a joystick on Earth, but has to do everything automatically because the signal travel time is just so long. So what would have happened when you hit the atmosphere and rush in with 20,000 kilometers an hour?
So basically, you use the atmosphere as to slow down. You hit the atmosphere, and so you then have a heat shield in order to keep the lander actually cool. So this heat shield actually gets really hot because of the impacting on the atmosphere, and that takes the majority of the velocity down. But then, as it's going into the thicker part of the atmosphere, you still need to go even slower, and so then you deploy some parachutes, and these parachutes then they slow the lander down even more. And then for the very last section, you ignite some rockets for a particular length of time in order to just come to almost zero speed as you hit the surface. So a lot of things have to happen one after another. Everything has to function perfectly in order for you to land gently and safely on the surface. And obviously that doesn't seem to have happened in this case, though we're still hoping.
Any guesses?
I would say that it does look like, for some or other reason, that it thought it had landed earlier than it seems to have done, and then the sequence then failed, and then it probably would have landed too hard. If it free fell the last kilometer or so, that would be enough to destroy it, I'm afraid.
So
yes.
So 1/3 of a G would not be sufficient to slow down. I mean, it's still accelerating from more than 1 kilometer altitude, and that means going at terminal velocity if no miracle happened in between.
Yeah, that's right. So it's not looking optimistic at the moment. But I think no one's gonna call it just yet. I think they will still, the European Space Agency will still try to communicate with it until they're pretty sure that the batteries have died, which I believe will be at least a few days from now.
All right, so let's skip ahead 4 years, and obviously the rover will not be able to land with a sky crane like the MSL Curiosity did a couple of years ago. So can you talk a little bit about the rover? This is, I think, really an exciting thing. We never had a rover on Mars from Europe. Although maybe from the design point of view, there are still a few things we have to learn. But just from the visual point of view. However, this machine is a very elaborate one. I remember one instrument which is on board, which is the Wisdom radar, and there's even some Austrian connects to this, because the one of the calibration campaigns for measuring the ice below the surface has been done in a subsurface environment in Austria, in an ice cave. Actually, a couple of years ago, we were participating in this measurement campaign. Now, that's just one instrument. So, John, can you elaborate a little bit on what kind of instrument we can expect from the rover, which is not so small, although not yet the size of the Curiosity lander, which will also be landing down in 2020 again?
Yeah, well, I think the interesting thing about the various surface landers missions to Mars is that they normally always have some kind of new goal to improve our understanding of Mars, and each one tries to complement what we learnt on the last time. And as I said, one of the important things about this rover is that it has a quite sophisticated drill system, which will allow it to drill under the surface and hopefully access material that maybe includes organics, which is very, very important. If we're to ever find life or signs of life or anything, then a first step towards that is to discover organics. And this is why understanding what's under the surface is important, because it does appear fairly sterile.
Why is that? I mean, couldn't you just search for complex organic molecules on the surface instead of digging? Because that seems to be a pretty elaborate technology we need for that.
They have done. So Curiosity has also looked for organics, and up until now, we have not found organics on the surface of Mars. Mm-hmm. And it seems to be it's a hostile environment for organics. There's a lot of UV light that we don't even have. We're protected a little bit by our atmosphere from the very hard UV from the sun. This does not happen on Mars. So there's a lot of hard UV on the surface of Mars, and it does seem that the surface of Mars is kind of oxidizing, which is also dangerous, destructive to organics on the surface. So when we want to find organics, and if we want to find possibly water or even liquid water, then we have to go underground. And that's why it's important to understand what's underground, especially where the ice is, and try to get at it. Yeah.
Well, there's one experiment which has been performed a couple of decades ago, actually, the labeled release experiment on board the Viking mission, which is an experiment where they were also looking for metabolisms on the surface, and had basically a radioactive marked nutrient fed to the soil, and there was a strong reaction going on, and it was pretty fast discarded as a chemical reaction without biological participation. However, I understand that the PI from back then still is not convinced about that interpretation, and I just understand that in the journal Astrobiology was a recent article where he basically revisited those arguments and said, well, I'm not convinced it's sterile. So what is your take on that? Because it's certainly a debatable experiment, which is remarkable for the time, but seemed to have stirred quite a controversy. So what's your take on that?
Well, yeah, I would say that it's still controversial in the sense that the results of those experiments are hard to reproduce in the lab now. But what I would say was that most scientists studying Mars would agree that it's some kind of interesting, complex geochemistry going on. My personal take on it is that I think there's due to the unique nature of the surface and due to erosion of the surface sand, I think that the minerals on the surface of Mars have become in some way activated, and then they do chemistry, add organics to it, and that is essentially what was seen in the Viking mission at that time. But it's not trivial to explain all of the results that they saw.
Given all the laboratory infrastructure which is available nowadays, and we have a fairly good understanding of the mineralogy of the Viking landing sites, would that be something which is reproducible in the chamber right behind you? Or is this so an advanced chemistry that we are just lacking a few clues exactly what to replicate?
We haven't used our chamber back here, or rather we haven't used it in any novel way that's helped our understanding. But what we have been doing is that if you take the minerals on Mars and you erode them, let's say to essentially crush this material down. So this requires, for example, if the wind transports sand on Mars and erodes it down, it seems to be that the minerals become activated in a way that isn't that usual. And why don't we see this on Earth? It's because on Earth, these eroded minerals, activated minerals, will normally become deactivated with water, but this doesn't happen on Mars. So what I think is at least that there are these activated minerals sitting around on the surface of Mars that are unusual for us on Earth, that we don't encounter normally. And they can perform some chemistry given the right conditions, and they were given the right conditions under the Viking experiments. And so I think what we have to do now is we have to do more simple experiments. It's not worth trying to recreate the Viking experiments because they were kind of like too complicated. One of them, for example, they were adding the soil to a complex organic mixture they called chicken soup. So this is not, this is a too complicated system in order to try to understand. And I think so. Then we have to break it down into more simple, simple chemistry.
I understand.
Yeah, I would say that we don't understand it right now. We don't understand everything about the surface chemistry of Mars right now.
Let's dare to take a few bold predictions, and let's say that the first human to walk on Mars is already born, and we're talking about a time frame of 20 to 30 years from now. And that was actually a user question I'm rephrasing here is, in what terms do you think that a human explorer, and a human explorer would obviously bring a lot of large-scale instrumentation with them, would they change the way we understand the surface? Is there topics where you say, as a planetary researcher, well, heck, if I had 50 kilograms of instrumentation payload with an intelligent human being behind this instrument, what would be the big questions you would tackle which are not tackable with robots at this point?
Well, there's really a lot that you could do really quickly if you had a human being in a lab. It's really hard to recreate the flexibility. Then what we can do very simply in the lab in a matter of minutes or hours, you simply can't even make a robot to do that, or it would be a huge task. So there are some things that human beings will be able to learn quite quickly, I think. For example, about surface chemistry and what's going on and what's it all made of. But I think we have learned a huge amount from sending robots to Mars, and we are still continuing to learn a lot. And I think if all we want to do is to just learn all we can about the surface of Mars, then there isn't really any reason to send human beings. We would send human beings to Mars because we want to explore Mars and we want to inhabit Mars. I think that's the driving force of why we want to send people to Mars. And I think every space agency on Earth are agreed on that goal, that that is what's interesting, to send people to Mars and bring them home again, like we did
Absolutely.
with the moon.
I couldn't agree more on that. I think wherever there are frontiers and limitations, there are always humans who will try to push this a little bit further. And that, I think, is a very nice outlook and conclusion, actually, on this thing with us. It's been great talking to you. And it's quite impressive thing you have in the backdrop here. I would love to see it one day with my own eyes, I have to say.
You're very welcome.
Oh, thank you very much. Denmark is not so far away from Austria. So, ladies and gentlemen, that brings us to the end of this webinar. This has been a webinar from the Europlanet Research Infrastructure, a European Commission-funded research program under Horizon 2020. My name is Gernot Groemer from the Austrian Space Forum, and I'm looking forward to see you for our next webinar in November on this very channel. Thank you very much. Have a good night, and let's keep our fingers crossed for Caparelli. Good night.
Thanks. Good night.